Hello and welcome to this next topic of OCR A Level Chemistry. This is topic 23, acids, bases and buffers. And the first thing we've got to do is talk about what a Bronsted-Lowry acid is. And a Bronsted-Lowry acid is the name given to what you'd probably think of as an acid, which is a proton donor, or an H+ donor. A Bronsted-Lowry base would be a proton acceptor. So we've talked about strong acids and weak acids before, saying that strong acids completely dissociate when in solution and weak acids only partially dissociate. So what actually happens if you put a strong acid into solution? What happens is the acid protonates the water, as in it donates a proton to the water. And the water accepts that proton using a lone pair, so it makes a dative covalent bond to the H+. So you end up with Cl- and H3O+. And this happens because the HCl is a stronger acid than water. So it's more acidic, so it donates a proton to the water, so that makes the water H3O+, so the extra H+, and the hydrochloric acid loses the H+, leaving just Cl-. Now here, the HCl is the acid, because it's the one that's donating a proton, and the water is the base, because it's the one that's accepting a proton. And because it's a strong acid, you say that this goes all the way to the right-hand side, and so you get a complete dissociation of the hydrochloric acid. And that's the assumption we make. It's not perfectly true. The equilibrium does sit very, very far to the right, but it is still an equilibrium reaction, and so it is possible for these to go back to make that. It's a dynamic equilibrium where the equilibrium position sits very far to the right, so far to the right that we assume it's 100% complete. But, as I said, it is in equilibrium, so the reactants can go back to form the products. And in that reaction, the H3O+ donates a proton to the Cl-, forming HCl and leaving H2O. And so, in this situation, the reverse reaction, the H3O+ is the acid and the Cl- is the base. And you can see that HCl and Cl-, one of them is an acid, one of them is a base, and they differ by an H+. The same is true with the water. H2O is a base, and H3O+ is the acid, and they differ by an H+. And those acids and bases which differ by an H+, we call those conjugate acid-base pairs. And you can be asked to label those acid-base pairs, and you could do it like this: acid-base linked by a line, or you can write acid 1 and base 1, and then base 2 and acid 2. Just to show you which ones are linked with which ones. And it's the one with the H+, which is the acid, and the one without the H+, which is the base. Now, it won't have escaped your notice. I'm sure that acids, some of them have 1 H+, some of them have 2 H+, some of them have 3 H+, so HCl, H2SO4, or H3PO4, so phosphoric acid. Those are called monobasic, if there is 1 H+, dibasic if there's 2, and tribasic if there's 3. Now the rest of what we're going to do is going to use only monobasic acids, so just assume, unless told otherwise, that they all just lose 1 H+. In the last topic I talked about equilibrium constants, so Kc was the equilibrium concentrations of the products divided by the equilibrium concentrations of the reactants, all raised to their stoichiometric coefficient as a power. Now, because these are also equilibrium reactions, we can write equilibrium constants for acid dissociation. They're called acid dissociation constants, and they're given the symbol Ka. And they all follow the same basic outline. And it's the concentration of the dissociated acid, so the H+ concentration, times by the negative ion concentration, divided by the concentration of the associated acid, so the one that hasn't yet split up. And it's not particularly useful for strong acids because we just said that they completely dissociate. But for weak acids, the acid dissociation constant is very useful. And knowing its value is very useful as well. So this is the basic equilibrium I'm talking about. This is the associated acid, and then this is the dissociated acid. For all of these, A- is just the rest of the acid. The H+ is always there because it's an acid. The A- is just the negative part that goes along with that H+. So Cl- in this case, or CH3COO- if it was ethanoic acid. And there's a good reason why we care about this acid dissociation constant, and it's all to do with this H plus concentration. Because from the H plus concentration, we can calculate the pH of a solution. And the way you do that is by entering it into the equation that I'm going to put up on the board now. And this is that equation. It says pH is equal to minus the logarithm of the H plus concentration. Now, don't worry about logarithms if you don't do maths, but log is a button on your calculator. So if you know the H plus concentration, then you just do minus, press that button, and write the H plus concentration. So say your H plus concentration is 0.01 moles per decimeter cubed, you'd write minus log 0.01, and that gives the answer of 2. So that would be a pH of 2. And occasionally you'll need to go back the other way, so you'll be given a pH and you want to work out H plus concentration. To do that, you do 10 to the power of minus whatever the pH is. So to use the same example as before, H plus concentration would be 10 to the power of minus 2, and 10 to the power of minus 2 is 0.01. So 0.01 is the concentration of the H plus ions. And now before we go into actually calculating pH and how you do it for different types of acids and bases, I need to introduce one more term, and that one's called Kw, and it comes from the acid dissociation constant for water. So water can act as an acid, and when it does, you get H plus and OH minus. And this happens in normal water solutions as well. So some of the water is split up, so it's not H2O, but it's H plus and OH minus. And because water is special for acids, then we use this equation to make one more constant, which is called the ionic product of water. And what it is just Ka, which is the acid dissociation constant for water, multiplied by the concentration of water. Now, the concentration of water in all aqueous solutions is pretty much the same. So you can make a new constant by multiplying these two together, and we call that Kw. And now we're almost done, so Kw is just the concentration of H plus ions times by the concentration of OH minus ions. And in pure water, H plus ions and OH minus ions are equal in their concentrations. And it's because the H plus and the OH minus both come from splitting up water. So if you split one water molecule up, you get one H plus ion and one OH minus ion. And so those concentrations have to be the same. And we know what they are because we know the pH of water. And the pH of water is 7. That means that the H plus concentration must be 10 to the power of minus 7. And OH minus must also be 10 to the power of minus 7. And that means that Kw must be 10 to the power of minus 14. And we can use this not just for pure water, but for any aqueous solutions. So in any aqueous solution, the product of the H plus concentration and the OH minus concentration must be 1 times 10 to the power of minus 14. But the first thing we're going to do is calculate the pH of some strong acids, because they're the easiest ones because they completely dissociate. So I'm going to use hydrochloric acid as an example. Hydrochloric acid, let's say it's 0.1 molar, and I'll work out the concentration of 0.1 molar acid, or hydrochloric acid. Now, because of our definition of strong acids, we can assume that 0.1 molar HCl would produce a solution with 0.1 molar H plus concentration. That's because every single HCl would split up to make an H plus, and so we're going to have 0.1 molar H plus concentration. And if I've got 0.1 molar H plus, I can use that to calculate the pH, because pH is minus log of H plus concentration. So that's minus log of 0.1. And if you put that into your calculator, it comes up with a pH of 1. So 0.1 molar HCl has a pH of 1. And that's true for all strong acids. You just take the concentration of the acid, do minus log of that concentration, and that tells you the pH of that acid. Only works for strong acids. Next we're going to talk about strong bases. Strong bases is very similar because strong bases completely dissociate. Your examples of strong bases are any hydroxides. So let's work out the concentration of 0.1 molar sodium hydroxide. So the same as with strong acids, we can assume that strong bases, if it's 0.1 molar sodium hydroxide, that means that it's 0.1 molar hydroxide. And that's because every single sodium hydroxide would split up to make sodium 1 plus and hydroxide. Now this is where it gets a little bit more difficult because this is not POH, it's pH. And so first of all we need to calculate the H plus concentration. But I said in any aqueous solution, this is true. the H plus concentration multiplied by the OH minus concentration is always 1 times 10 to the power of minus 14. So I now have to plug that into this equation to work out H plus concentration. So that's 1 times 10 to the power of minus 14 divided by 10 to the power of minus 1, which gives you 10 to the power of minus 13. And to work out pH, we do pH is minus log of that, which gives you the answer 13. Now there's also a bit of a cheat way, and if you do maths you might want to prove this, but if you treat hydroxides as if they were acids, like H pluses, then you can work out the POH by just doing minus log of the OH minus concentration, and then subtract that number from 14. So if I'd have treated this as an acid, I'd have ended up with 1 as my answer, the same as down here. And then if you do 14 minus 1, that gives you 13, which is the answer we worked out. I won't go through how to do that because this isn't a maths video, but give it a go if you're a maths student. And you can use it, but be careful when you use it because it's not the proper way of doing it, and you might lose marks if you write things down wrong or if you don't get the answer correct in the end. This way, at least if you get halfway through, then you might get some of the marks for the question. If you use the other way and you don't show exactly what you're doing, then you won't get any marks. Okay, so that's all the relatively simple ones done. Now I'm going to talk about weak acids and buffers, and those are much more complicated. So I'm going to do weak acids first, and for weak acids, I need this Ka expression. So I've left it on there, and I want to answer this question. What's the pH of 0.1 molar ethanoic acid? And to calculate that, we need to know the Ka of ethanoic acid. So I've said it is 1.76 times 10 to the power of minus 5 moles per decimeter cubed. Now that number's a lot less than 0, so you can expect that mostly it'll be reactants. I'm just going to write out this Ka equation. This is the standard one, so generic for all acids. Let's just write it out for ethanoic acid, just so we know how. Okay, so that expression would be H plus concentration, because that's always in there. And then this is the negative ion that goes along with the H plus. So if you look at ethanoic acid, it's CH3COO minus, and then an H plus. And that's the H plus from the carboxylic acid group, the COOH group. And then this will be the associated acid, which is just HA in this. And the question says that the Ka is 1.76 times 10 to the power minus 5. So we know that this is equal to 1.76 times 10 to the power minus 5. But we want to know the pH. And to work out pH, I need to know H plus concentration. So I want to really know what this is. But to do that, I need to use these two as well. So I need to know what the associated acid concentration would be and what the concentration of the negative ion would be. Now, if we assume that there's only one thing in solution, and that's the ethanoic acid, because that's what they've said to us, then the same way as we did for water earlier, you can assume that the concentration of H plus is equal to the concentration of the negative ion, because for every one of these which splits up, it makes one H plus ion and one A minus ion. So those concentrations must be the same if this is the only thing in solution. And if H plus concentration and CH3COO minus concentration are the same, that means that I'm just multiplying H plus concentration by H plus concentration, which means H plus squared. And now let's talk about this. This is the associated acid. Now because this number is so small, 0.000176, that's an equilibrium constant, remember. And it shows you where the equilibrium position sits. And that is far to the left. I mean, mostly nothing is dissociated. In fact, it's going to be about 1 in 10,000 that have dissociated. So you can assume at this level of accuracy, just 3 significant figures, that the concentration of the associated acid hasn't changed enough that we need to talk about it. And so we assume that the concentration of this is 0.1 molar. And that's nice now because there's only one unknown. And that unknown is the one we wanted to know in the first place, the H plus concentration. So you've got to rearrange for H plus concentration. So it would be 1.76 times 10 to the power minus 5 times by 0.1 and then square rooted would give you H plus concentration. That concentration comes out to be 1.3266 times 10 to the power minus 3. Then to find pH, you just do minus log of that answer. And to 3 significant figures, that is 2.88 as a pH. I use 3 significant figures because this was 3 significant figures and that was 3 significant figures. And that's how you do it for all weak acids. So if you have a weak acid solution and you want to know the pH of that solution, you need Ka. Without Ka, you can't answer the question. And once you've got Ka, you need to make 2 assumptions. Those assumptions are the H plus concentration is equal to the A minus concentration. And the second one is that the concentration of the associated acid doesn't change, or at least it doesn't change significantly. Now what happens as the Ka increases is that more and more of the acids are dissociating. And so that second assumption becomes less and less true, because at some point this number is going to get big enough that the equilibrium position shifts far enough to the dissociated side that this concentration is no longer going to be 0.1. It might be 0.099 or 0.098. And the stronger the acid is, the more that decreases because it's being dissociated. And so the less and less true this becomes. And so that's one limitation of this method. It's only useful for weak acids. Next up, we need to calculate the pH of buffers. But before that, I need to tell you what a buffer is and how it works. And it's a solution that has a specific property. And that property is that it minimises changes to pH when you add a small amount of acid or alkali. So if a strong acid or strong alkali is added to a buffer, the pH doesn't change much. If you add strong acid to water, for instance, the pH very quickly changes from 7 to like 2. So if I took 100 millilitres of water and added 1 milliliter of 1 molar acid, then the pH goes down to like 2 from 7. But if I added the same to a buffer at pH 7, then the pH would barely change. And a buffer is made by having a mixture of a weak acid and its conjugate base. So, for example, a weak acid could be ethanoic acid, and its conjugate base would be the ethanoate ion. And if I mix together significant quantities of the acid and the base, then you end up with a buffer. And you need to be able to explain how this mixture minimises pH changes on the addition of small amounts of strong acid or strong alkali. And to do that, we need this equilibrium reaction. This is the equilibrium reaction we use to write the acid dissociation constant, because it's just the acid dissociation of ethanoic acid. And you can see that this is the acid, and this is the conjugate base. And so what we need to do is explain what happens if we add small amounts of acid or small amounts of alkali. So, if we add small amounts of acid, then it reacts with this CH3COO- to produce small amounts of CH3COOH. That shifts the equilibrium position left slightly, but never really changes the pH of this solution, because it's only a small change in equilibrium position. So that's how it deals with H+. It reacts the H+ with the conjugate base, making the conjugate acid. Now if we add OH-, what happens? Well, OH- would react with the conjugate acid, creating the conjugate base, and shifting the equilibrium right slightly. And because these equilibrium shifts are very slight, then you end up not changing the H+ concentration very much, and therefore not changing the pH very much. Now the pH change is obviously dependent upon how much acid you add, and also how much of the acid and the base is already in the solution. But this explanation is good enough for the marks of a 5-mark answer. And hopefully you can see where they come from. The first one is for the equilibrium, then there's 2 for the addition of acid, what happens and what effect it has on the equilibrium, and then 2 for the addition of alkali, so what happens and the effect on equilibrium. So now we know how they work, we need to be able to calculate the pH of a buffer given how much of the conjugate acid and base are in that solution. Now, there's 2 ways on the spec to make a buffer, and the first one would just be mixing together the acid and, say, sodium ethanoate as a salt. That would get you your acid part and your conjugate base part. And the second way is to react excess acid with a strong base. So when you react acid with base, you make the salt, and you're left with excess acid left over. So that would be the acid and the salt in solution together. And that's the way I'm going to explain. Okay, so here's the question. What's the pH of the solution which results from the reaction between 100 centimetres cubed of 0.1 molar ethanoic acid and 50 centimetres cubed of 0.1 molar sodium hydroxide? The Ka of ethanoic acid is is 1.76 times 10 to the power of minus 5. I'm going to make one quick change. I'm going to change this to 50.0 centimetres cubed. So there's all three significant figures. Alright, so how do we calculate that pH? Well, we want to know H plus concentration. And because it's a weak acid, then we need to use the Ka formula. Obviously, because it's given us Ka also. Now this actually looks very similar to the way that we answered a weak acid question, but you can't answer them the same way. You can't make the assumption that H plus concentration is equal to CH3COO minus concentration, because the buffer contains extra CH3COO minus. When we did it with weak acids, that was the only thing in solution. When we're doing it with buffers, there's more than one thing in solution, so you need to take those all into account. The first thing we've got to do is do the reaction. So there's a reaction between acid and base, and we need to do a reaction between those two and work out how many moles of each thing we've got. Okay, so this is a reaction. It's going to go fully to completion because it's a strong base. And I'm just going to write in the number of moles of each. So for the ethanoic acid, it's 100 centimetres cubed of 0.1 molar, so that's 0.01 moles. And for the sodium hydroxide, it's 50 centimetres cubed of a 0.1 mole solution, so that's 0.005 moles. And so from this, you can see the ethanoic acid is in excess, and the limiting factor is the sodium hydroxide. And so all of this will react to produce sodium ethanoate. So you'll end up with 0.005 moles of ethanoate ions. You'll also end up with 0.005 moles of water, but we don't take that into account. And 0.005 moles of the ethanoic acid will also have been used. So that's going to end up with 0.005 moles of that left. But these are amounts, and we need concentrations. The volume of the solution is going to be 150 centimetres cubed. So we divide these by 0.15 decimeters cubed to work out the concentrations, and then we put these values for concentration into this equation. So the concentration of ethanoic acid is 0.0333, the concentration of ethanoate is 0.0333, so there's the same and cancel each other out, which leaves us with H plus concentration being equal to Ka, and that is 1.76 times 10 to the power of minus 5. Therefore, we can calculate the pH by using this equation, so pH is minus log of that answer. And to three significant figures, that is a pH of 4.75. Now, if you think about this, actually, it doesn't matter how much of each of those you've got, it doesn't matter what the concentration is particularly. What actually matters is the ratio. So some questions just ask you for ratio. It doesn't matter if both of these concentrations are 2 molar, they still cancel each other out. What actually matters is how many times more of one you've got than the other. And so it's the ratio of ethanoate to ethanoic acid which determines the pH. And the way you change that would be by having more of an excess or less of an excess of the ethanoic acid to begin with, because then there's more or less left over at the end. Now the carboxylic acid one, specifically ethanoic acid, is quite a common one that comes up. The other common one that comes up is the pH of blood, because the pH of blood is controlled by a buffer solution, and that buffer solution is hydrogen carbonate ions and carbonic acid. So hydrogen carbonate is HCO3-, carbonic acid is H2CO3, and those two, or the ratio of HCO3- to H2CO3, controls the pH of the blood. So if you get a small amount of strong acid in your blood, it doesn't change the pH too much, because changing the pH a lot in your blood would affect all of your body systems. And so that pH has to be maintained at a very narrow range. And those are the questions where I've seen the ratio come up before. And when I say ratio, I just mean this number divided by that number, what is it? If this is twice that, then that's a ratio of 2 to 1. If this is 5 times that, then it's a ratio of 5 to 1. And so in a lot of ways, it's easier to answer those questions because you've just got 3 unknowns then, the ratio, the H plus concentration, and the Ka. And so you're given Ka in the question, or you can calculate K in the question, and you're given H plus concentration in the question, or you can calculate it from pH, and then the ratio is the third thing that's left. Now there's one more thing we've got to do for acids, bases, and buffers, and that's talk about neutralization and neutralization curves. So I'm going to get rid of this and draw up the neutralization curves. What I mean by neutralization curves is how does the pH change in a neutralization titration, for example. So if I have a strong acid and I add a strong base to that, how does the pH change as I add more base? Say I've got 25 centimeters cubed of a 1 molar acid and I'm adding 1 molar strong base to that. How does the pH change as I add that base? And the same for strong acid, weak base, weak acid, strong base, and weak acid, weak base. Now let's just say that our strong acids have a pH of 1, our strong bases have a pH of 13, and our weak acids have a pH of 4, and our weak bases have a pH of 10. How would each of these graphs look for these 4 reactions? And these are what you'd get. So when you add a strong base to a strong acid, the pH starts at 1, and it gains slightly, and then suddenly it will jump to a high pH. And this happens very quickly on the addition of just a couple of drops of strong base. If you react a strong acid with a weak base, then you still get the same jump, just doesn't go quite as high or as steep. For the addition of strong base to weak acid, you get very similar. It starts at 4 though, if it's a weak acid, goes to 13. And then the last one, going from 4 to 10, and this graph doesn't go very steep at all compared to these other ones. So it takes more addition of weak base to get a big pH change. And for each of these, you get exactly the opposite shaped graph, by starting at the top and going down if you were adding acid to base. And why do we care about this? Well, this is very useful when you're conducting titration, for instance, neutralization, acid-base titration, because you want your indicator to suddenly change at exactly the right point, and then you can be very accurate with your titrations. And there's lots of different indicators, indicators which change at different pHs. And so you need to know exactly what pH your big change is at, your quick change, in order to choose the right indicator. And that point, right in the middle, where the pH change is quickest, so the rate of that pH change is fastest, that is when you want your indicator to change colour. So indicators are all in an equilibrium reaction, and that equilibrium reaction is very dependent upon the pH, or the H+ concentration. So they are themselves conjugate acid-base pairs. The conjugate acid will be one colour, the conjugate base will be the other colour, and that the specific concentration of H+ ion that makes them change, that's when you get a colour change. So the only difference between the red and the yellow, for instance, is that one of them's got an H+ on it, and the other one's not got that H+ on it. And this point I talked about earlier, the point where they suddenly change, is called the equivalence point. And it's different depending on whether it's strong acid, strong base, or weak acid, strong base, or strong acid, weak base. And it depends upon the concentrations of the solutions. And so there's loads and loads of different things you can get. These are just the 4 basic ones. But I always chose 1, 10, 13, and 4. And what if the pHs were slightly different? You get a different shaped curve. And so for each of those curves, you need to find the equivalence point, which is the point right in the middle, the steepest part. And that is the pH that you want your indicator to change at. Or, to use correct grammar, that is the pH at which you want your indicator to change colour. And you'll be disappointed to find out that that is it for this topic of acids, bases and buffers. Thank you for watching, and I hope you can join me for the next one. Goodbye.